Assalamu alaikum. Welcome to Aflak channel. This is the second episode from a series of episodes explaining how to calculate prayer times. Each episode in this series will have two versions, one in Arabic and one in English. This English version has captions in English. You can enable this from the settings below. I can also use the auto translation feature, and here let me choose French for example. And you can use the automatic translation to choose from tens of languages supported by YouTube. The first episode of this series covered conversions of units in astronomy calculations. It explained the effect of atmospheric refraction on observations and also explained how an observer height can change the results of calculations. This episode will explain how to calculate Dhuhur prayer time or noon time, because we will understand three methods to calculate Dhuhur time. But let's begin. Dhuhur prayer time starts when the center of the sun passes the meridian. Some scholars prefer to add 1 minute or more to make sure that the shadow starts forming on the eastern side of building. Although most applications and calendars do not add any time. We will calculate the time the sun passes the meridian, and it's your choice to add 1 or more minutes, and we will add a facility for that. The formula to calculate Dhuhur time is dt equals 12 plus tz minus ln over 15 minus EOT over 60. dt is Dhuhur time in hours or noon time in hours. 12 is midday or 12 noon. Tz is the time zone of the location, which is the time difference between the location and Greenwich Mean Time GMT, or the new name UTC, Coordinated Universal Time. Time zone is positive for regions east of Greenwich and negative in the west. Let's note that some countries that use summer time have two different values for the time zone, depending on the time of the year. So we need to use the time zone in effect on the date that we're calculating the prayer time for. In addition, some large countries have more than one time zone. And in this equation, we use the time zone of the region we are calculating prayer time for. LON is the longitude of the location where positive numbers are east of Greenwich and negative numbers are west of Greenwich. And finally, EOT is the equation of time, and this will be the focus of this episode. dt here is calculated in hours. If we want to convert it to a portion of a day, we divide everything by 24. And because EOT is the only one that changes continuously, we will calculate this part as MT, where MT is the mean time, the average Dhuhur prayer time throughout the year. And then dt becomes MT minus EOT divided by 60 divided by 24, or simply MT minus EOT over 1440, because EOT is measured in minutes, and 1440 is the number of minutes per day. If we implement this in Excel, and we will use Mecca as an example, LON, or longitude, we'll use longitude of Mecca 39.8262. Next is the time zone, TZ, and the value is 3, because Mecca is GMT plus 3. Dhuhur mean time, or MT, equals 12 plus time zone minus longitude over 15, all divided by 24. And we can use Excel time format, and this will be the average Dhuhur time through the year. To know Dhuhur time on a specific day, we need to know the equation of time value for that day. Let's have the date here. Use 1/1/2025. The next step is to know the value of the equation of time for this date and this longitude. Let's assume the value is minus 3.63. And by the way, this is the correct value. We can calculate Dhuhur time dt as MT minus equation of time over 1440. This will be Dhuhur time. The rest of this episode will focus on how to calculate the equation of time. But let's start by knowing what is the equation of time. The equation of time is the difference between the time in our watches and the position of the sun in the sky. And there are multiple ways to know the value of the AUT for a specific longitude on a specific day. This episode will explain three methods and the error margin in each method, where the last method is the most accurate but most complex. The first method is the most primitive, although not very bad. This method is to use a table to know the value of the equation of time for a certain date. So in the left column we'll have the date, and I use the year 2000, and we can use any other year. And column B is the value of the equation of time for that day. We can also use a chart like this that shows the value of the equation of time versus date. or a chart like this that also adds the declination of time. And all of these will give us the same result. Now in column C, I will add the month multiplied by 100 plus the day of the month. So the value 101 is the first day of the first month. I'll copy this value and paste it for all days on that year. So 105 is the 5th day of the first month, 420 is the 20th day of the 4th month, and so on. We note here that column C does not contain the year because this method assumes all years are the same. But let's see an example on how to use this method. If we return to the example of Mecca, let's use the date 1/1/2025. We'll take the month, multiply it by 100, and add the day, and the result is 101. Now for the equation of time, we will do a lookup of this value in column C and return column B. And the result is minus 3.25, almost. Dhuhur time, MT minus EOT over 1440, and the result is 12:23:57, with a difference of 23 seconds from the correct value. This method is simple, but there is an error margin that can reach up to 50 seconds, which is almost 1 minute. This error margin is true for 20 years. If we calculate Dhuhur time for a period more than 20 years, the error margin will exceed 1 minute. If this error margin is okay and suitable for your purpose, you can use this method. The second method is an equation. If we search Google for equation of time and go to Wikipedia, we'll find these two equations. EOT equals minus 7.659 sine D plus 9.863 sine 2D plus 3.5932, where capital D is 6.24004077 plus 0.01720197 multiplied by 365.25 multiplied by year minus 2000 plus small d, where small d is the day number of the year. 1st of January is number 1, 2nd of January is number 2, and so on. Now let's do this in Excel. The date, and we'll use the same day in the previous method, 1/1/2025. To calculate the day number, we need to calculate the first day of the year, FDY, and we'll use the function date. We'll use the year of the date given. The month will be 1 and the day will be 1. And this will give us the first day of the year. Now small d will be the date minus first day of the year plus 1, which is equal to 1 because 1st of January is the first day of the year. Now we need to calculate capital D, which is equal to 6.24004077 plus 0.01720197 multiplied by 365.25 multiplied by the year from that date minus 2000 close bracket plus small d and close the bracket, and the result is 163.33. The value of d here is in radians, so equation of time is minus 7.659 multiplied by sine d plus 9.863 multiplied by sine open bracket 2 multiplied by d plus 3.5932, and the result is minus 3.53. And Dhuhur time MT minus EOT over 1440, and we see the difference here is 6 seconds from the correct value and 17 seconds from the first method. We can change the date to 9/9/25 in both methods, and we'll see that the small d will be the day number of that year, and we get the results for Dhuhur time in the two methods with a difference of 24 seconds. The second method also has an error margin close to the error margin of the first method, which can exceed 50 seconds. However, this method has an advantage. It helps us understand the reasons behind the equation of time. If the Earth rotates the Sun in a perfect circle with zero inclination, this will mean that the Sun will return to the meridian after 24 hours, or 86,400 seconds. The equation of time will always be zero, and noon time will never change. But the fact is, the Earth rotates the Sun in an elliptical orbit with an axis inclination of 23.4 degrees. The axis inclination effect will make the day length on the vernal equinox in 20th of March and the autumn equinox on 23rd of September 23 hours, 59 minutes, and 40 seconds. On the summer solstice on the 20th of June and the winter solstice on 20th of December, day length will be 24 hours and 20 seconds. Those seconds will add up to 9.863 minutes, plus or minus. The elliptical orbit also affects the day length. On 3rd of July, when the Earth is closest to the Sun, day length will be 23 hours, 59 minutes, and 52 seconds. On 3rd of January, the Earth will be in the farthest distance from the Sun, and day length will be 24 hours and 8 seconds. These differences will accumulate, and the maximum effect is 7.659 plus or minus. If we add these two effects, we'll see that the equation of time will range from minus 14.2 to 16.4. So noontime will be earlier by 16.4 minutes and later by 14.2 minutes. And if we go back to the equation of time formula, as we knew, d is calculated in radians, and it will be easier to convert this to degrees. The first number is 6.24004077 multiplied by 180 over pi. This will give us the result in degrees. Second number is 0.01720197 multiplied by 180 over pi. And this will give us the result in degrees. The angle 357.528 is the angle from the last perihelion, when the Earth was farthest from the Sun. If we subtract this from 360, we get 2.472, which is the angle the Earth needs to rotate to return to the perihelion again, which is about 2.4 days from 1st of January. The second number, 0.9856, is the angle rotates every day relative to the aphelion and perihelion. And if we divide 360 degrees by this number, we get 365.25964, which is the number of days the Earth takes to move from one perihelion to the next. And it's different from the number of days in the calendar year. And if we go back to the equation of time formula, we can see that it has two terms. The first uses sine d, while the second uses sine 2d plus 3.5932. If we see the value of d through the year, we can see that it reaches 0 on 3rd of January, which is the perihelion, and it reaches 180 on 3rd of July, while the second term 2d plus 3.5932, we see that it increases until it reaches 360 or 0 between 20th and 21st of March, the vernal equinox. It starts increasing until it reaches 180 on 20th of June, which is the summer solstice. It continues to increase until it reaches 360 or 0 on 20th of September, which is the autumn equinox. And it increases again until it reaches 180 on 20th of December, which is the winter solstice. And this is the effect of the inclination of the Earth axis. We can draw the chart for the effect of the elliptical orbit of the Earth and the chart for the inclination of the Earth axis. If we add these two charts, we'll get the equation of time in red. Now let's move to the third method, and as we knew, it's the most complex, but we'll take it step by step. We'll open a new Excel file. We'll call this sheet main. We'll open another sheet and we'll call it calc for calculation. Now we'll go to main and we'll define a few things first. LON, longitude. We'll use Mecca 39.8262 and we'll call this cell LON. Next is TZ or time zone. And we'll use the time zone of Mecca, which is GMT plus 3. And we'll call this TZ. Next is MT or mean time, Dhuhur mean time through the year. And this is equal to 12 plus TZ minus LON over 15, all divided by 24. And we'll use time format. And this will be Dhuhur mean time, and we'll call it MT. In our calculation, we need to convert from degrees to radians. So we'll define DEG here, and this will be equal to 180 over pi. This is to convert from radians to degrees. We'll call this DEG. Next is to convert from degrees to radians. So we'll call this RAD, and the value is pi over 180, and we'll call this RAD. Now let's go here and define some cells. First is date, then we will define the cells for prayer times that we will calculate in the coming episode. Fajr, sunrise, which is not a prayer time but the end of Fajr time. Then Dhuhur, Asr, sunset or Maghrib time, and then Isha. Let's use the same date, 1/1/2025. We'll go to Calc and we will take the date from the main sheet. So we have the date here. In astronomical calculations, we do not use dates. Dates include years and months, which have different values and different lengths, so they are difficult to handle. So instead, we just use the number of days passed from a specific reference. And the reference we'll use in our calculation is called Epoch 2000 or J2000. And we have a number of values that determine the location and movement of celestial bodies on 1st of January 2000 at 12 noon time. It's like a snapshot of the celestial bodies' positions and movements. And Epoch 2000 was not the first one. There was 1950 and 1900, but we'll use J2000 because it's the latest. Now to use J2000, we need to find the number of days passed since 1st of January 2000 noon time. And note that we count the days from 12 noon, not 12 midnight as we are used in our daily life. The number of days passed can also have parts of a day, which is the number of hours and minutes and seconds passed after 12 noon. And the time we use here is Greenwich Mean Time. Luckily, Excel stores date as numbers. So if we take any date and we use number format, it will give us the number of that day. And the number here represents the number of days since 1st of January 1900. So the date 1st of January 2025 is number 45658. Now if we put the date 1st of January 2000 at 12 noon time and we convert this to a number, the result is 36,526.5. So we can find the number of days passed since 1st of January 2000 noon time. All we need is to subtract the date minus 36526.5. And this will give us the number of days passed from 1st of January 2000 noon time until 1st of January 2025 midnight. Next is to calculate the ED for the mean time. So it's equal to this number plus MT minus TZ over 24 to convert this to Greenwich Mean Time. And this is the result. This method uses the difference between two things. The first thing is the perfect circle orbit. If the Earth rotates the Sun on a perfect circle with no axis inclination, the Sun will move the same angle every day, and there will be no difference in noontime between one day and the other. But the fact is, Earth rotates in an elliptical orbit, and it covers different angles at different times. And also the axis inclination has an effect. So the equation of time is nothing but the difference of these two. The blue dot is the perfect circle orbit, while the red dot is the actual orbit. And we note that the red dot sometimes passes the blue dot, sometimes it goes behind. EOT is nothing but the difference between these two orbits. So we need to calculate the blue orbit or the perfect circle orbit, and then calculate the red orbit and subtract it. So GML or geometric mean longitude, which is the perfect circle orbit, is 280.459 plus 0.98564736 multiplied by ED. This assumes the Earth rotates the same angle every day. But we need this number to be between 0 and 360. So we'll use the mode of 360. And this is the perfect circle orbit. Next, we'll calculate the geometric mean anomaly. And this is equal to 357.529 plus 0.98560028 multiplied by ED. And this is the elliptical orbit effect. Next, we'll calculate EL, which is the ecliptic longitude, the longitude of the Sun on the ecliptic grid, and it's equal to GML plus 1.915 multiplied by sine GMA, convert to radians, plus 0.02 multiplied by sine 2 multiplied by GMA, and convert this to radians. And the number 1.915 is almost equal to the 7.5 minutes that we saw in the second method. but this is in degrees. We need to multiply it by 4. Next, we'll calculate RA, or right ascension, which is the actual orbit. And this is equal to A tan 2, open bracket, cosine EL, convert to radians, comma, 0.91751 multiplied by sine ecliptic longitude converted to radians, close to bracket. We notice the number 0.91751. This is the cosine of the Earth's axis inclination, 23.4353. And RA is the actual orbit. RA is calculated in radians, so we need to convert to degrees. We notice it's negative, so we need to add 360, and then we use mod of this number of 360. And this will make the angle between 0 and 360. And this will be the actual orbit of the Earth. So EOT is nothing but the perfect circle orbit minus the actual orbit, all multiplied by 4 to convert to minutes. And DT, or Dhuhur time, is MT minus EOT over 1440. And this will give us Dhuhur time. We'll use time format. And this will be Dhuhur time for this date. We'll go to the main and we'll move the value here from the calc sheet. And we'll use time format again. And this will be Dhuhur time on this date. Now, if we compare this to stellarium, which is a good application, first let's change the location. We'll put the latitude of Mecca, which is 21.4225, and this will not affect the calculation. The longitude is 39.8262 east. Now we'll change the date to 2025, month 1, day 1. And we'll move the time until the sun reaches the meridian line. The hour angle HA should be closest to 24 or 0. The azimuth should be closest to 180 or 0. Dhuhur time in Excel was 12:24:20, stellarium 12:24:19, with a difference of 1 second. We can also check the ecliptic longitude and the right ascension between Excel and stellarium, but we notice a difference. One of the reasons of this difference is that we calculated EL and RA using the time MT, not the actual Dhuhur time. So if we change the time in stellarium to 12:20:42, which is equal to MT, we can see that the difference between EL and RA calculated in Excel and stellarium, the difference is 2 over 10,000, which is very small. We can change the date to 15th of March 2025, and we get 12:29:34. We can change it to 5th of May 2025, and let's compare these two values to stellarium. So we can change the month to 3, the day to 15, and move the time until the sun passes the meridian, and the difference is 2 seconds. We change the date to month 5, day 5, and again we change the time until the sun reaches the meridian, and the difference is 1 second. But there are a few issues with Excel. First is the earliest day that can be used in Excel is 1st of January 1900, because this is day number 1, and you cannot use any date prior to this. The second issue of Excel is that it considers the year 1900 as a leap year. So if we put 1st of March 1900 and we subtract 1, we get 29th of February 1900. But there is no such a date. 1900 is not a leap year. So we cannot use any day prior to 1st of March 1900 in Excel. But what if we want to use an earlier day, or if we want to use a programming language other than Excel? We'll use something called the Julian day, which is used a lot in astronomical calculations. First we'll do year, month, and day, and we'll use the same. Year 2025, month 1, day 1. First we need to modify the year. If the month is greater than 2, so 3 and above, we'll use the year as it is. Otherwise, if it's 1 or 2, we'll subtract 1 from the year. We also need to modify the month. If the month is greater than 2, we'll use the month as it is. If it's 1 or 2, we need to add 12 to the month. So the first month of 2025 is like the 13th month of 2024. It's like the month goes from 3rd to 14th. And because the Gregorian calendar went through a correction in 1582, we need to add a correction here. And the correction is 2 minus integer of the year divided by 100 plus integer of the year divided by 400. But we only need this correction if the date is after 14th of October 1582. So we'll add a condition here. If year multiplied by 10,000 plus month multiplied by 100 plus day. If this is greater than 1582, month 10, day 14, then we'll use the correction. If not, we'll use 0. And finally, we'll calculate JD or Julian day. And the formula is integer of 365.25 multiplied by the year here plus 4716 close to brackets plus integer of 30.6001 multiplied by month plus 1 close to brackets plus day plus correction minus 1524.5. And this will be the Julian day for 1st of January 2025. Now to calculate the epoch day, all we need to do is use the year 2000 and day 1.5 because we need 12 noon time. And this will be the JD for 1st of January 2000 at 12 noon time. So all we need to do is the ED equals JD minus 245.1545. So if we go back to year 2025, day 1, we'll see that the ED equals 9131.5. Now let's go back to the calc sheet and we'll copy these cells and we'll paste here. This is the ED, so we'll take it from here and we can see that, and let's go to main and change this date to 1st of January 2025. And we can see that the results are identical. So we'll go back to the main sheet, we'll copy these cells and we'll paste them here. And we'll take Dhuhur time from calc sheet and we'll use time format. Now we can change the date to any date. We're not limited by Excel. So we can use the year 1000. If we go back to Stellarium and use the year 1000, month 1, day 1, and move the time until the sun reaches the meridian, we can see that Excel is 47 seconds and Stellarium is 59 seconds with 12 seconds difference. We can use 500 BC, for example, or we can use the year 7000. Here we are not limited, we can use any date. Now, if we keep the year 7000, and what we will do is we'll copy these cells and we will paste them on a new Excel sheet, but we'll change this to be equivalent to 1st of January, year 7000. And then we will copy these cells. The first line is 1st of January, so we want this to be 2nd of January, so we'll add 1 to this. And then we will copy this row and paste it for 365 days. So these are the values for the full year of the year 2000. If we take the equation of time and we put a chart here, let's make it smaller, let's remove a title. This is the equation of time chart for the year 7000. If we compare this to the chart for the year 2000, we can see that there is a big difference between the two. So the equation of time value does change through the year. Finally, we'll add the option to add minutes to Dhuhur time. We call this DM. And in here, we will add the Dhuhur time minutes divided by 1440. We'll also do the same here. We will add Dhuhur minutes divided by 1440. So now if we want to add 1 minute, for example, we can put 1 here or 2 or any value we like, but I'll keep this to 0. As an additional information, we can actually calculate the difference between the sun and the earth in astronomical units. The value is 1.00014 minus 0.01671, and this is the eccentricity of the earth orbit multiplied by cosine GMA converted to radians minus 0.00014 multiplied by cosine 2 multiplied by GMA converted to radians. And this is the distance in astronomical units. To convert to kilometer, we need to multiply the AU by 149,597,870.7, and this will be the distance in kilometers. And if we compare this to stellarium, we can see that the difference is about 3,000 kilometers. So in summary, we have seen three methods to calculate Dhuhur time: the lookup method, the formula method, and the more accurate calculation method. And we also calculated the distance between the Earth and the Sun. There are other methods to calculate the equation of time with much more accurate results, error margins of fractions of a second for a long period of time. But these calculations are much more complex because they calculate a number of parameters that change with time but very slowly, like the inclination of the Earth axis, the eccentricity of the orbit, and so on. But I think the third method is accurate enough for prayer times, with a margin error of 1 or 2 seconds, especially if we consider that most applications and websites show prayer times in minutes and not seconds. So they have an inherent error margin that can reach up to 30 seconds. In the next episode, we'll explain the calculation of Asr prayer time and the use of spherical triangle. I wish you find this episode useful. Please subscribe, share, and enable notifications. Thank you. Until next episode, keep safe. Thank you very much, and see you in the next episode.